Hello AP Statistics students. In this video we're going to take a look at a few more characteristics concerning statistical experiments. There's a few more parts that we haven't talked about. So here they are. In this video we are going to identify confounding variables, describe factors and levels in an experiment, and recognize replication. So remember, the big picture here with statistics is two things, all right, in statistics. All right, we are trying to figure out something about a population, and there's two ways to do that. You can do an observational study or an experimental study. Now, we've done a lot of observational study. Now we are moving on to experiments, and in an experiment, you have a response variable and an explanatory variable. This is basically the same as it was when we did regression lines and two-variable analysis with scatter plots. Your response variable is simply your outcome. The thing you're trying to figure out, the thing you are trying to predict somehow, usually. Okay, and your explanatory variable is what you are going to use to do that prediction. All right, use to do prediction. You can also think of it as the thing you are going to change. All right, what are you going to change in your experiment? Also sometimes known as the treatment. And so you do this study and you then measure the outcome, the response variable. All right, one quick thing about observational studies, though, that I think we forgot to mention before. There are two types of observational studies, retrospective and prospective. So retrospective is simply using existing data to do your study. Also think of it as looking backwards. All right, prospective is the exact opposite. That's looking forwards, okay? So here in a prospective study, you are following people or subjects into the future. Now that one can sometimes be a little confusing because it might sound like an experiment because you're following these people, you're tracking them, but you're not trying to change them. All right, the big thing about an observational study is you are just observing or asking questions, and you can do that through the future. Continuing to follow people and track their progress without actually changing anything. Now, as soon as you prescribe them something, now you're doing an experiment because you're actively trying to change them instead of just tracking them. All right, so here we are. Here's our first example where we can start taking a look at some of this. So in a study of more than 4,700 children, researchers from Cincinnati Children's Hospital Medical Center found that those children whose mothers smoked during pregnancy were more than twice as likely to develop ADHD as children whose mother had not smoked. All right, let's stop right there for a second and decide, what is this? Is this an experiment? Is it an observational study? Is it a retrospective or prospective observational study? Which one is it? So first off, definitely not an experiment, okay? You cannot assign or tell somebody to smoke during pregnancy. That would be wildly unethical. So this cannot be an experiment. That's one of the problems with studying the effects of smoking is you can't do an experiment with it because it would be wildly immoral and unethical to assign people to start smoking. So this is definitely an observational study. All right, we are just looking at people who are already doing these things. Now, is it retrospective or prospective? Now, here it gets a little iffy because the intro here doesn't really tell us which one it is. And so let's imagine how it could be either one. All right, if it was a retrospective, less likely, I think, but here's where you would be going into medical records. And you would just look. All right, you just found medical records and you were looking through and finding some sort of relationship between smoking and ADHD in mothers and their babies. Probably not what happened, because you probably wouldn't have access to people's medical records like that, but it could be possible. This one was probably a prospective study. All right, so what probably happened was they identified 4,700 mothers who were about to give birth. They agreed to be in the study, and they followed these people for a couple of years. So they followed and asked survey questions of these mothers for a few years. Now, even though the study is done, it would still be a prospective study because they followed them over a couple of years and asked them questions and basically kept track of them. But I guess it could have been retrospective if they just went into medical records in the past. Hard to say. That wasn't really the purpose of this example, but I thought it was a good thing to call out. All right, what this problem was about was something called confounding variables. All right, so explain how confounding makes it unreasonable to conclude that a mother's smoking during pregnancy causes, there's the big word there, causes an increased risk of ADHD in her children based on this study. So what this study is trying to make us think is that smoking leads to ADHD. And it certainly seems like there might be a relationship there, but that doesn't necessarily need to be true. There could be other reasons. The confounding variables are the other reasons that this could be happening. Okay, we talked about this in scatter plots a lot. This was the whole, very similar to the saying that correlation does not imply causation. All right, so we need to identify, hey, what could a third variable be that connects these two, okay? What could another variable be besides smoking that could relate the smoking and the ADHD? So we're going to kind of go this way and then back to this way. And what is another variable? And so one that the book had for this as well, maybe it is a poor diet. All right, I'm not saying I have to prove that it is. I'm saying that it could be. And now I simply relate these three variables, and that is my confounding variable that I'm saying, hey, it could be this instead of smoking. So the way you do this is I have to relate all three. If mothers who smoked were also more likely to have a poor diet. So there I connected my explanatory variable, the smoking, to this other variable that might actually be the cause. If the ones who smoked were also more likely to have a poor diet, it could be the poor diet that causes an increased risk of ADHD. And so there, I connected it now to my response variable. So you have to make the connection to both the old explanatory and the response for this new third variable that might be the cause. All right, so hopefully you can see the two parts to that sentence. The first part, I connected it to the explanatory variable, and the second part, I connected it to the response variable. All right, that's sort of your criteria for talking about confounding variables. And that's why most observational studies cannot lead to a causal relationship. All right, one more here. This one is one that you've talked about before. I think you saw a AP classroom video on this. Does higher attendance lead to higher test scores at high schools? According to the newspaper Boltman B, schools with more than 97% attendance are more likely to have high test scores. That sounds pretty good. Explain why this observational study cannot establish a cause-effect relationship. All right, pause the video there, see if you can write something. Did you pause the video? Try to write something. All right, there's many reasons why this cannot necessarily be a causal relationship. There's just too many confounding variables. So you could say something like, there are confounding variables that could be causing higher test scores instead of attendance. Now, that's not enough. I have to give an example of one possibility. That was just sort of an overall general statement. So it could be that schools with high attendance are also, and here you got to think, what other thing could be relating attendance with high test scores? Two of the things that came to my mind were affluence, all right, how rich is the school, in a better neighborhood possibly, and then other one is how big is the school. Smaller schools would usually have higher attendance rates than big schools, and it's possible that smaller schools have higher test scores that are causing higher test scores. Either one of those are possible. I just have to connect those ideas to the response variable and to the explanatory variable, okay? Are also in more affluent neighborhoods, and being in an affluent neighborhood is causing the higher test scores. All right, now in terms of affluence and how much money people have, that is just a huge long list of other confounding variables. Having more money does not make you smarter, certainly, but it does come with so many advantages. Those are all confounding variables. So that's kind of a catch-all idea there, is the idea of affluence. But it is a possibility. The main thing there is that you are connecting this other possible variable to both the explanatory and the response, okay? All right, so that is confounding variables. Those are huge things. They're big issues, especially in observational studies. How do we get rid of some of them? Well, that's where experiments come in. Experiments try to lessen possible confounding variables, and we'll show you kind of how. The first thing we want to talk about with these experiments are factors and levels of variables, okay? So we can't just stop with the explanatory variable. oftentimes it goes deeper than just one explanatory variable. Okay, especially in an experiment where you are trying to control for many options, you're trying to limit the number of confounding variables, you're trying to take care of all of those, you have to test more than just one thing. So we break that up into factors and variables. So your factor are simply your explanatory variables. And oftentimes you will have more than one. Your levels are different values the explanatory variable can have. All right, those are sort of general statements. That'll make sense when we do one example. You have factors, and you kind of have the levels of those factors. So here's my example for that. Mr. Bolt has gained a few pounds during COVID-19. You've probably heard of the freshman 15. Well, Bolt has the COVID 15. But the diet starts now, right now. He has recently heard how great the keto diet is. But Bolt is no fool. He is going to experiment on others before he tries this new diet. He gets 30 volunteers to try, why did I have that in air quotes? I don't know. To try either the keto diet, a vegan diet, the South Beach diet, or a control which will not change their diet at all. And participants will either be assigned to follow the diet strictly with no exceptions, or loosely where they are allowed to cheat once a week. Mr. Bolt wants to know if he can still have his donuts. All right, so what do we have here? So we've got two variables here, and it might be kind of hard to pick them out. The two variables, or factors, we've got our diet and whether or not they're allowed to cheat. Okay, so that would be how strict do they have to follow this diet? I don't know, is strictness a word? That's kind of hard to pick out the two variables. The two things I am changing here are what diet you're having and how strict do you have to follow that diet. Those are my two factors. Those are my two explanatory variables. But underneath those, they each have different levels. All right, so the diet can be broken up into three different levels: the keto diet, the vegan diet, and the South Beach diet. The strictness can be broken up into two different levels. All right, very strict, or people are allowed to cheat every once in a while. All right, so I hope that kind of helps. We've got the factors are your explanatory variables, sort of the big ideas: diet, strictness. And then the levels are different types of those. All right, they're different levels, for lack of a better word. I know it's bad to use a word in its own definition, but there you are. All right, so there's three different types of diets, and there's two different levels of strictness. And so, plus, I guess you could even put the control over here. There's no real levels of control, but so total, how many treatments do we have? Well, we've got three different types of diets and two different levels of strictness. 3 times 2 is equal to 6 treatments plus the control. All right. Because people will get the keto diet, and some of them will get the keto diet and have to be strict. Some of them will get the keto diet and they'll be allowed to cheat. All right, so that's actually underneath the keto diet, there are two combinations. So 2, 4, 6 total treatments plus the control. All right, That's kind of a simpler one. Let's move it up a notch from there. Ah, the 5-second rule. We all know and love this one, right? We've all been in places where the 5-second rule definitely doesn't work. My house that I rented with roommates before I got married, the kitchen floor was definitely a no 5-second rule. That floor was so gross. If it came within 2 inches of the floor, you threw it away. I don't even care if it touched it or not. If it just got close to the floor, you threw it away. That floor was gross. Happens when you have 4 guys living in one house. All right, problem. Have you ever dropped a tasty piece of food on the ground and then quickly picked it up and eaten it? If so, you probably thought about the 5-second rule, which states that a piece of food is safe to eat if it has been on the floor less than 5 seconds. Sometimes 10. The rule is based on the belief that bacteria need time to transfer from the floor to the food. But does it work? Researchers from Rutgers University put the 5-second rule to the test. They used 4 different types of food: watermelon, bread, butter, and bread with butter, and gummy candy. They dropped the food onto 4 different surfaces: stainless steel, ceramic, tile, wood, and carpet. And they waited for 4 different lengths of time: less than 1 second, 5 seconds, 30 seconds, and 300 seconds. Finally, they used bacteria prepared in 2 different ways: in a tryptic soy broth or peptone buffer. I have no idea what that is. Once the bacteria were ready, the researchers spread them out on the different surfaces and started dropping food. All right, so here we go. What are our factors and levels in this here experiment? Much more complicated. Well, first, we've got the different types of food. So here are our factors. All right, we've got food. That was one thing they are changing. All right, doesn't matter what type of food you are dropping. Then they were testing surfaces. All right. Then they thought about, all right, length of time was another variable they were testing. And the last variable they had was how the bacteria was grown. All right, so what about each one's levels? How many levels of food were there? Well, they had watermelon, bread, bread with butter, and gummy candy. So there were 4 levels here. All right, watermelon, bread, bread with butter, and gummies. Surfaces, how many surfaces? 4 different surfaces here. So that also had 4 levels in terms of surfaces: stainless steel, ceramic, wood, and carpet. 4 different levels there. Time, how many different times? Oh, they also had 4 different time lengths. So the time also had 4 levels. Less than 1 second, 5 seconds, 30 seconds, and 300 seconds were our 4 levels for there. Bacteria, looks like they only had 2, right? 2 different types or ways of preparing bacteria. So that one only had 2 levels. We had the soy broth and the peptone buffer, whatever the heck that is. So one kind of interesting is how many treatments do they have to do? There's a lot of combinations. Let's take a look at a combination. Here's one treatment. All right, one possible treatment would be, hey, let's do watermelon on, let's say, ceramic tile for 30 seconds with bacteria from the peptone buffer. All right, that is just one treatment. There are lots of combinations here, right? To figure out how many, you just multiply them all. So total treatments You do 4 times 4 times 4 times 2. I believe that gives you 128 different treatments. So in more and more complicated experiments, you definitely have more explanatory variables to keep track of, and sometimes those explanatory variables have different levels to keep track of, and those all become different treatments you're trying to track and get data on. All right, last thing here for today is the idea of replication in an experiment. Now this it's important, it's kind of weird. You don't really have to do anything with it besides recognize it and say something has it or not. So this is one of those weird times when a math word isn't the same as that word is used in colloquial English. All right, replication for most people means to replicate, to do it again kind of thing. That's not what it means in stats. All right, so I might say this is not repeating an experiment. It's tempting to say that, but that's not what it is. And you can guarantee if I give you a multiple choice question about replication, that would be one of the options, because I want to know, do you realize it is not repeating an experiment? Okay? In stats, replication means you have enough individuals or subjects so the change you observe is coming from the treatment and not pure chance / variability. All right. Think of the results replicating themselves in your experiment enough that what you see and observe is not coming from chance, but from whatever treatment you prescribed. So let's take this example here about our 5-second rule. All right, there's 128 different treatments here. If I only did this experiment 128 times, that means one gummy bear for each one slice of watermelon, one slice of bread, and I did each of these combinations only once, something weird could have happened that one time I dropped the bread. All right, and that's not really going to give me great data. If I only do each treatment once, I need to do each treatment many times. So this one treatment that I described here, watermelon on ceramic tile for 30 seconds with bacteria from peptone buffer. I would have to do that one treatment many times to really trust my data. If I only did that treatment once, something weird could have happened, and it could have been pure chance that I got whatever outcome I got. So it's mainly, are you using enough subjects? Now, they don't tell us how many they did here, so I can't really make an assessment on replication, but hopefully they did this experiment a couple hundred times so that each treatment had 5, maybe 10 iterations. Let's see here. All right, Bolt. 30 people here. All right, if I got 30 people and I had 6 treatments plus a control, I'm only having maybe 5 people do each type of diet. That's not too bad. If I have 5 people being strict on the keto diet and they all had success, I doubt that would be because of chance. That might be a little low. 30 might be a little low. If I'm having 6 treatments, 30 might be a little low. I might want to up that to maybe 100. Then I'd be pretty good. Any volunteers? Anyone else? I don't think we have any more experiments. This one, while there is no replication in observational studies, they try to have massive sample sizes to kind of get around that. But just, are there enough subjects in your study? There's no golden rule like, hey, 14 is too little and 15 is just right. It's not like that, and I'm not going to try to split hairs with you that way. It's more of, hey, you only had 1 person per treatment. That's not enough. Oh, you had 50 people per treatment? That sounds much better. All right, I'm not trying to split hairs here with the replication. Just obvious enough, trying to be obvious. Are there enough people in each treatment so that pure chance is not what you are seeing? All right, so those are some of the last things we have to clear up about experiments in general. All right, so I'm hoping now you can identify confounding variables, describe factors and levels, and recognize replication.